Section 1-4, trapezoid rule. The objective of this section is to estimate the value of a definite integral by dividing the region under the graph into trapezoids and summing the areas. If you recall in the last section, we were approximating definite integrals by counting squares. The difficulty that we had with that was the fact that we were all coming up with slightly different answers. We were close, but we were all getting slightly different answers. And the reason for that was because of the fact that we were using different approximations for the areas of those partial squares. It was also related to the fact that some of us were using more squares and other people were using fewer squares, also plays into that as well. The advantage that we're going to see with trapezoids is that as long as we all are using the same function, the same interval, and the same number of trapezoids, we're all going to get the same answer. It'll still be an approximation, but we're going to see that it's more formula driven then. Okay? All right, let's remind ourselves of what a definite integral is before we get too far here. If you recall from the last section, we said that a definite integral is the signed area between the function and the x-axis. Now, the reason why we say it's the signed area is because of the fact that it can be positive or negative. Depends on the function and the interval, etc., but it could be one or the other. The other thing we said in the last section is that it turned out that the definite integral is the product of x and y. And we found that because in that first example that we did, we saw that to find the area of that region, we were actually taking a horizontal distance, your x, and multiplying it by a vertical distance, your y, and thus finding the area under that curve there, which is the definite integral. So it's a product of the x and the y that gives us the area, which of course is then the definite integral. That's a big difference then between a definite integral and a derivative. The derivatives that we talked about in the first two sections in this chapter, we are finding that a derivative is actually just slope. It's a change in y divided by a change in x. That is, we're taking the quotient of y divided by x to find a derivative, versus a definite integral here is a product of x times y. Big difference between the two. Now the objective explained the technique we were going to use here, and the technique that we're going to use this time to approximate the definite integral is by finding the area of trapezoids. And so we've got to refresh our memory here perhaps a little bit about the area of a trapezoid. So let's do that here real quick. Here I've got a sketch of a trapezoid for us. This trapezoid has two right angles. Now, of course, that's not part of the definition of a trapezoid. By definition, a trapezoid is just a quadrilateral in which it has one pair, exactly one pair, of opposite sides that are parallel. Okay, and those parallel sides we call the bases of that trapezoid. So here I have those two bases labeled as B1 and B2. Those are the two parallel sides. Now it turns out the trapezoids we're going to work with will actually have two right angles, and that's the reason why I've sketched it that way. And that's actually very convenient for us, because in order to calculate the area of a trapezoid, you need to know the height of that trapezoid, which is actually the distance between the two parallel sides, between the two bases. So with the fact that those are two right angles over there, that third side actually is the height of the trapezoid. Turns out very nice. So down below there I have our formula for the area of a trapezoid is 1/2 the quantity B1 plus B2 times H. In other words, it's the average of the bases, B1 plus B2 divided by 2 in essence, times the height. All right, so there's our formula for how we are going to calculate the area of a trapezoid. Now, I'm going to take this trapezoid, you'll see in a second, and we're going to take and rotate it 90 degrees counterclockwise, and we'll slide that underneath our function. So let me give you an example of what that will look like here. Here we've got a sketch of a function. I'm going to call my function here f of x. And you can see that I've got a trapezoid sketched underneath that function. Notice the two points on the trapezoid touch the curve there at the top. In fact, I'll go ahead and sketch in or mark in here these two right angles so you can see where those ended up there when I rotated it 90 degrees and counterclockwise and slid it under that curve. And so I need to find the two bases and I need to find the height. Now in this case, the two bases are actually vertical here. They're the parallel sides, but they're the vertical sides of this trapezoid. So let's name this point right up here. We'll name that as A, f of A, because of the fact that that occurs at A on the x-axis there. That means that the x value is at A, and I can find the y value by plugging in A into my function and thus getting f of A. I can do the same thing over here at B, and we'll name that point as B, f of B. Now the significance of that for us is this. If I were to measure, which is what I need to do, measure this base of this trapezoid, that is, I'm measuring the distance from the x-axis to that point on my curve. And that's exactly what the y value tells me. It tells me how far I am from the x-axis. That's what the y value is. So in other words, f of A is actually base 1, B1 from our original trapezoid. And I can do the same thing over here at B, that if I want to measure this side of the trapezoid, f of B tells me the length of that second parallel side, that base 2. And the last piece that I need then is the height, which is this distance right here along the x-axis. And I, of course, can measure that. I know A and B. We call this, though, delta x. Delta x, and of course, delta is the Greek letter delta that we're talking about. We use that many times in math and science to represent a small change. That's the uppercase Greek letter delta. So delta x is saying a small change in x is what it's indicating there. So now that I know my two bases, f of A and f of B, and I know my height, delta x, I can calculate the area of that trapezoid. It's 1/2 the quantity f of A plus f of B times delta x. So now that we know how to calculate the area of a trapezoid that's placed under a curve, we're now going to expand that and look at the trapezoid rule. So here's our trapezoid rule, and actually I'm going to sketch a function here for us to work with. And it really doesn't matter what function, I guess, that you have, but I'm going to sketch one that's got a little bit of a curve to it, I guess, but it really doesn't matter if it's got a curve or not. And I'm going to say that this over here is A. That'll be our starting point. We'll say that this over here is B. That's our ending point. And our goal, of course, is to calculate the definite integral, which is the area between the signed area between our function and the x-axis. All right, so let's go through the steps of how we actually go through this process here, and that's what we're going to do. We'll go through the steps, and we'll keep filling in some information from our on our sketch up above. So the first thing that we want to do is subdivide the interval from A to B into n subintervals. All right, so I'm going to try to divide this up into n subintervals. I'm going to try to make these equally sized, although it might not look like that, but that's what I'm intending to make. I'm not going to worry about drawing all of these, so I'll just say dot, dot, dot. It continues. Just put an ellipsis in there for that indication. And so let's say that we've got this now divided into n subintervals. So now the next step of this is to calculate the width of each one of those subintervals. And of course, to do that, it's a very simple calculation here. I just need to figure out how big the interval from A to B is, and then divide it by how many subintervals I split it into. So in other words, I calculate delta x by taking B minus A, that's the width of the interval, divided by n, which is the number of subintervals that I've split it up into. That'll tell me the width of each one of my subintervals. Okay, we'll use that, of course, in our calculation, because we need to know the height of our trapezoids, and that's what delta x is going to represent for us. In fact, let me go ahead and sketch that in each one of these here. So in other words, this distance right here is delta x. This distance right here is delta x. This distance right here is delta x. I'm intending for those all to be equally spaced. This distance right here is delta x. All right, let's take a look at the next step of our process here. to help us with finding the area of each trapezoid or the naming of the parts that we need. We're going to name these points and the ends of our subintervals. Let x sub 0, x sub 1, x sub 2, all the way up to x sub n be the boundaries of these subintervals. So we'll go ahead and name these. Now realize that A also has another name then. It's also known as x sub 0. This would be x sub 1 and x sub 2 and x sub 3 and so forth, all the way up to x sub n minus 1. And B would be at x sub n. That's another name for B. So we'll just name those to make it a little bit easier to write our formula down for our calculation. We need to have those x values named. And then the last step of this is really to calculate the area of each trapezoid and sum it up. So if I sketch in my trapezoids that I end up with here, I'm going to do this in green. Here's my first trapezoid that I see. Something like that. And my next trapezoid looks something like this. And the next one looks something like this, and so forth, all the way up to the very last one here. Notice this very last one looks like it's going to actually extend above the curve here slightly. Some of these trapezoids are completely below the curve, some might be above the curve. And so we want to calculate the area of each one of those trapezoids. Now remember, to calculate the bases of these trapezoids, the parallel sides, it turns out that this is equal to f of x sub 0. This is equal to f of x sub 1. This is f of x sub 2. This is f of x sub 3, and so forth, all the way up to the very last ones are at f of x sub n minus 1 and f of x sub n. Those heights. All right, so we can calculate the area of all these trapezoids and add them up. So we call this, because it's trapezoid rule, we call it T. And because we're using n trapezoids, we write it as T sub n. So let's calculate the area of that very first trapezoid there. Scroll back up here. It has a base of f of x sub 0 on the left, a base of f of x sub 1 on the right, and a height of delta x. So the very area of that very first trapezoid is 1/2 f of x sub 0 plus f of x sub 1 times delta x. There's the area of that first trapezoid, one down. Move on to the next trapezoid. For the second trapezoid up here, notice that it has heights, or bases really, of f of x sub 1 and f of x sub 2. Those are the two parallel sides, two bases. And again, the height is delta x again. So it's plus 1/2 f of x sub 1 plus f of x sub 2 times delta x. And we'll add on the next one here. To go to the next line here, it's 1/2 of f of x sub 2 plus f of x sub 3 times delta x. And we'll just say this continues there. We only drew the first three trapezoids, so that's all I'll worry about writing down is the first three here. All the way up to the very last trapezoid, and if you want to see what the sketch looks like, again, to remind yourself of it, notice that the bases of this last trapezoid are f of x sub n minus 1 and f of x sub n. So it's going to be 1/2 f of x sub n minus 1 plus f of x sub n times delta x. And there we go. That's how we find the area of all of these trapezoids and add them up. The only thing I don't like about this is it's a little bit cumbersome to write this out every single time. If there was a way that I could kind of simplify this formula, it would be really nice. And that's what we're going to work on in the next couple of steps here. Let's see if we can simplify this a little bit. So one thing that I notice here in this formula is that each one of these I'm multiplying by delta x. So I'm going to go ahead and factor that out front here. I'm going to pull that delta x out front. Now you might also look at this and say, well, each of these have a 1/2, and I got a different idea about the 1/2, so I'm going to leave that in for right now. So I'm going to factor out the delta x out front. And let's multiply the 1/2 through as we go here. So if we look at this very first trapezoid, we had 1/2 of f of x sub 0. So I'll go ahead and write that down. 1/2 of f of x sub 0. And still with the first trapezoid, we can see that we have 1/2 of f of x sub 1. And I can see on the second trapezoid that I have another 1/2 of f of x sub 1. 2 halves, of course, add up to 1 whole. So that means this is actually just f of x sub 1. That happens again here. I have another 1/2 of f of x sub 2. And I have the other half of f of x sub 2 right here. So those 2 halves make up just f of x sub 2. And I have an f of x sub 3 right here. And I didn't write down the next term, but the next term would have an f of x sub 3 there, another 1/2 of it there. So I end up with just another f of x sub 3. And so forth. This continues all the way up to the end. And in the very last, I guess I'll go ahead and write the last 2 terms of this. In the last 2 terms, I have a f of x sub n minus 1 that I have here. And in the term previous to that, I have the other half of that. So I end up with a whole f of x sub n minus 1. And then in the very, very last term here, I only have half of f of x sub n, the very last trapezoid there. So notice that it turns out we end up taking half of the first function value, f of x sub 0, and half of the very last function value, f of x sub n, but all the rest we just simply add those function values in between. All right, one last thing here that I'm going to do, and that's, you can see now I left the 1/2 in there. It actually makes that a pretty nice little formula. I'm going to rewrite this in one last way here. Actually, I'm going to adjust it a little bit 2 times here, but the first thing I'm going to do is rewrite f of x sub 0 as just f of a. Remember, x sub 0, the other name for x sub 0, if I go back up here to our picture, is a. I'll leave the other terms alone, f of x sub 1, f of x sub 2, and I'm only going to write down the first 3 terms there. That's all you need to show me. And if there are more terms that go in between the first 3 terms and the last term, then you can do that dot, dot, dot thing here. Put in those ellipses to indicate that pattern continues here for us. All the way up to 1/2 of the very last one. I'll just worry about the very last term since it's different from the rest of the terms that are going to be written after that third one. We'll put half of x sub n is the same as b, right? So what I want to do was change the name there of my very first x value and my last x value back to their other name, which is a and b. And further, I'm going to do one last thing here, just because of the fact that you're going to see it written this way in your calculator program that you're going to use. This is equal to delta x times 1/2 f of a plus, to get to x1, realize if I go back up to my graph here, to get to x1, if I start out at a and I add on delta x to it, I'll end up at x sub 1. So in other words, a plus delta x is the same as x sub 1. So I'm going to write it that way. So instead of f of x sub 1, it's going to be f of a plus delta x. And x sub 2, again, starting at a, if I were to start at a, I'll draw this in a different color here so you can see it a little bit better. If I were to start at a and add on delta x and another delta x, I would end up at x sub 2. So another name for x sub 2 is a plus 2 delta x. So I'm going to write it that way, f of a plus 2 delta x. And so forth, all the way up to 1/2 of f of b. Oops. Okay, there's our formula. That's what you're going to see actually when you run your program on your calculator. It's going to show up in that formula. That's why I want you to see it that way. That's all right. All right, one last thing for us to note about this process. You saw that we used n trapezoids. It turns out that the more trapezoids we use, the better the approximation. The more trapezoids used gives a better approximation of this. All right, so let's try a couple of examples here and see what happens. Look at example 1 there on page 19. It says use trapezoids to estimate the definite integral of f of x equals negative x squared plus 90x plus 14. And we're going from x equals 0.1 to 1. And it says to use 9 increments. That's saying to use 9 trapezoids, 9 subintervals. They even say 9 strips there, however you want to describe it. Those all mean the same thing. All right, so let's write down our function here. F of x is equal to a negative 100x squared plus 90x plus 14. And we're going from x equals 0.1 to x equals 1. Now, if you recall, this is actually the same function that we used in our second example from the last section. So we've actually seen this same curve before. Let me just bring up the calculator so you can see what this thing looks like. I have in y1 that same function that we used in the last example of the last section. I have the same window we used, in fact, from 0.1 to 1 for the x's, and then from 0 to 35 for the y's. And we can graph that and see what it looks like. There's the graph for that thing. Okay? All right. So the first thing that I want to do is I want to draw a little sketch of what we're actually doing with this problem. You don't always have to draw a sketch, but I think I want to start out with a sketch for this first problem just so you see what we're doing. So the curve looks something like this. It really doesn't matter if I have an exact curve here, but we'll approximate it. This was at 0.1, and we'll say that 1 is somewhere over here. And we're dividing this up into 9 subintervals. So the first thing I'm going to calculate is what does delta x equal. Remember, delta x is equal to b minus a, where in this case the a is the 0.1, the b is the 1. So it's 1 minus 0.1 divided by n. N is the number of trapezoids. They said you split this up into 9 increments. So we're going to divide that by 9. So 1 minus 0.1 is 0.9 divided by 9 gives us an interval width of 0.1. Now what that tells me then is that first subinterval over here on my graph starts out at 0.1 and it ends 0.1 units later. That would be at 0.2. The next subinterval ends 0.1 units later, that would be at 0.3 and so forth. All the way up to the very last subinterval would end 0.1 units before 1, that would be at 0.9, and end, of course, at 1. Okay? And if you want to sketch your trapezoids in there to see what they look like, that'd be fine, but I just wanted to show you the corresponding x values that show up in this problem. All right, so now all I need to do is write down my formula. This is your work for the problem that you have to show. Show me the formula that you're using to calculate this definite integral. So the formula was it's delta x, so delta x is the 0.1, times 1/2 of my function evaluated at the first x value, which I can see from my graph up above is at 0.1. Also notice that that's the starting point for our interval. That'll happen every single time. Whatever that starting point for my interval, the a value there is what I plug in first. Plus my function at the next x value, which is 0.2. The graph kind of helps me see that, but also realize that if I take 0.1 and add this 0.1, that is add my delta x to my previous x value, that gives you the 0.2. Now I can keep doing that. Adding 0.1 onto 0.2 gives me 0.3, so f of 0.3 is the next x value. Again, you just need to write down the first 3 terms here. So I'll just say plus dot dot dot, and that's 1/2 of the very last x value, which is at 1. That's the b value. There's our formula. You can actually plug this into your calculator and just do this like from the home screen or something like that. But I gave you a program so that you could quickly do these calculations. So let's jump back over to the calculator. And I don't really have to graph this every time, but I do have to put into y1 the function. So you got to get the function into y1. And then we'll run our trapezoid program. And it's going to ask you, first of all, do you have an equation that you're using that's put into y1? Or do you have data that's stored in list 1 and list 2? If you have a function represented algebraically, then you put the equation in y1. If you have a function represented numerically, then you put the data into list 1 and list 2. We, of course, have an equation in y1. It asks you for the starting value. So we are starting at point 1. It asks you for the stopping value, the b value, that we're stopping at 1. And it's going to ask you for the number of increments, or the number of trapezoids, subintervals, whatever word you want to use to describe that. The n value here in this case is 9. And when you press enter, it'll bring up a little screen that will show you how you calculate delta x to remind you of that. And it also shows you how you calculate t sub n. It shows you the formula. There's no reason to not be writing down the formula right here on your sheet. You have to show that. That's your work. The program shows you exactly what that formula is. The only thing you need to do is actually put in the correct x values there. Don't leave it in terms of delta x and those a and b values. Actually plug in the right numbers there. Press enter again, and it will give you the results. It tells you the value of a, b, and n that you punched in. It also shows you the calculation for delta x in case you want it. And there's t sub n. It's 23.7. So this is equal to 23.7. Which is actually very close to the exact answer. The exact answer here technically is at 23.85. We're really close to that. More trapezoids will get us even closer. All right, let's take a look at one more example here. If you turn to page 21 in your book, example 2 is going to give us a function that's represented numerically. It says on a ship at sea, it is easier to measure how far you are going than it is to measure how far you have gone. Excuse me. Let me read that again. It's easier to measure how fast you are going than it is to measure how far you have gone. Suppose you are the navigator aboard a supertanker. The velocity of the ship is measured every 15 minutes and recorded in the table. Estimate the distance the ship has gone between 7:30 p.m. and 9:15 p.m. Okay? Now, first of all, your calculator can handle a set of data like this, and you can punch it into your calculator and run your program to evaluate this. But of course, if you're going to do that, you're not going to use 7:30, 7:45, and so forth. We're going to want to put this in terms of some numerical values. The other thing to consider here is that they've given us the velocity measured in miles per hour. So the fact that that's in miles per hour, the hour is the key there. That means that when I go to come up with some equivalent to these times, I'd want to use hours. So if I were to want to punch this in my calculator, I'd probably want to start this out at time 0. And this would be a quarter of an hour later. 15 minutes later is a quarter of an hour. And then this would be a half. This would be 0.75 and so forth. So if I was going to punch this in my calculator, these are the numbers that I would punch in. The 1, 1.25, 1.5, and finally 1.75 would be those values. Okay, if you tried to run the program and using the other set of data, your answer is going to be off because it's going to have some weird units there, and you don't want to do that. The way I calculate, though, this definite integral is the same way we just looked at. The key here is to understand why is it a definite integral that we're calculating. And the reason for that, let me just draw a quick sketch of this function. I've got my speed, which is measured in miles per hour. It's actually velocity measured in miles per hour that they said it was. On my y-axis, and I have my time, which is now measured in hours. I've converted those over to hours here for me, along my x-axis. And in order to get the distance that I've traveled, I know that the distance is equal to my velocity times my time. And I can see that my time, of course, is my x value. My velocity, of course, is my y value. So in other words, I'm taking and multiplying x, excuse me, that's y, times x. Or x times y, however you want to read that. So since it's a product of x and y, that's what leads me to say, okay, that's an area I'm finding to solve this problem. That's a definite integral then that I've got to calculate. That's the thought process I've got to go through to figure out that, first of all, it's a definite integral to find the answer to this question. All right, so let's calculate the definite integral. Now, they have a total of 1, 2, 3, 4, 5, 6, 7, 8 data values that they've given you. If you have 8 data values, that means you actually have 1 fewer subintervals, so you have actually 7 subintervals here. So we're going to calculate t sub 7. Now I'm going to write the formula 2 different ways here for you. The first way is going to look just like we saw in the last example. And the second way is going to be, I think, going to be a little bit more convenient for us since they've actually got the y value sitting here right in front of us. But let's go ahead and write it this way. First of all, I need to know the delta x, change in x. And actually I can see that from my values I've written down here that I know I'm starting at time equals 0 and then going up a quarter of an hour each time. So delta x, the change in my x, is 0.25. And then it's 1/2 my function at the first x value, which is at time 0, plus my function at the next x value, which is 0.25, plus my function at the next x value, which is 0.5, and so forth, all the way up to 1/2 my function at the very last x value there, which would be at 1.75. That's one way you can write this down. I think it's a little bit more convenient, actually, to do it this way, though, since, again, they have given you the y values. They're sitting right here in front of you in the table. I know what f of 0 is. F of 0 is right here. It's 28. So instead of writing f of 0, just write down what that value is. 1/2 of 28 plus f of 0.25 is the 25 that's in the table. F of 0.5 is 20, and so forth, all the way up to 1/2 of the very last value is 1/2 of 26 that we need. Okay? Now again, you could punch in the data from the table here into list 1 and list 2 and let your program crunch the numbers, but by the time you do that, you could have just punched in less data actually on the home screen and got the same answer. So I'm going to do it that way. So on the home screen, I'm just going to tell it to do this calculation. It's 0.25 times 1/2 of 28 plus 25 plus 20 plus 22 plus 7 plus 10 plus 21, and it's 1/2 of the very last value, 1/2 of 26. Which obviously the 1/2 of 28 and 1/2 of 26, you can do the math in your head and just type it in as 14 and 13 there, but I wrote it out for you. And we get 33. So 33 is our answer here. This turns out to be equal to 33. Not only that, we should be able to put units on this, and because of the fact that it's a product of x and y here, the units are a product of the x units and the y units. So the x units are in hours, and the y units were in miles per hour. Notice the hours cancel out, and we're left with just miles. So it turns out that this is equal to 33 miles. And that's how we calculate a definite integral using trapezoids.